Hello friends, this is 360 Degree Academy. Today we are going to study chapter 9 of class 11, that is Mechanical Properties of Solid. At first, rigid body. It generally means a hard object having definite shape and size. But in reality, a solid can be stretched, compressed or bent by applying force. Hence, solids are not perfectly rigid bodies. The deforming force. The force applied to change the dimension of the body. Elasticity. When the deforming force is removed, the body comes back or regains its original shape and size. This property by virtue of which a body opposes any change in its shape or dimension and tends to regain its original dimension when its deforming force is removed is called elasticity. Now, elastic body. A body which regains its original dimension when the deforming force is removed. Plastic body. A substance which partially regains its original dimension when deforming force is removed. Perfectly elastic body. A material which completely regains its original dimension when deforming force is removed. Perfectly plastic body. A material which does not regain its original dimension when the deforming force is removed. Anode. In reality, no body is perfectly elastic or perfectly plastic. However, quartz is considered as perfectly elastic. Elastic behavior of solids. Solids are made up of closely packed atoms or molecules which are bonded together by interatomic forces or intermolecular force. When deforming force is applied, distance between these forces changes, and when deforming force is removed, the force tends to push the atoms or molecules back to their equatorial position. Now, stress. Stress is equal to force upon area, which has the unit as Newton per meter square, that is equal to Pascal, which is denoted by the symbol Pa. Its dimension formula is kg meter per second square by meter per square. Types of stress. Tensile stress. If the body is stretched by the deforming force, the stress is produced is tensile stress. Compressive stress. If the body is compressed deforming force, the stress produced is compressive stress. Shearing stress. The restoring force per unit area produced in the body due to tangential deforming force is known as shearing stress. Volume stress. When the deforming forces are applied on the body normal to its surface, at each point there will be change in volume without any change in geometrical shape. Stress, that is equal to external deforming force by area, that is equal to F by A. Dimensional formula of stress, mlt minus 2 by L square. Therefore, that is ml minus 1 T minus 2. The SI unit of stress is Newton per meter square, that is equal to Pascal, same as that of the pressure. Now, the strain. Strain equal to change in dimension by original dimension. There is no unit for strain as such as stress, whereas strain is equal to delta L by L, whereas here delta L is change in dimension and L is the original dimension. Types of strain. First, longitudinal strain. The ratio of change in length to the original length of a body is called longitudinal strain. Strain is equal to change in length by original length for longitudinal strain, or delta L by L as denoted before. Here the symbol signifies the difference between two objects, that is of longitudinal strain. Tensile strain. If the length of the wire increases due to deforming force, the ratio of increase in length to the original length is known as tensile strain. Compressive strain. If the length of the wire decreases, the ratio of decrease in length is called compressive strain. Second, the shearing strain. The ratio of relative displacement, that is delta x, between the faces of a body to its length, L, is known as shearing strain. Third, volume strain. The ratio of change in volume of the body is known as volume strain. Now, elastic modulus. Elastic modulus can be defined as stress upon strain, and there are many types of elastic modulus. So let us study types of elastic modulus. First, Young's modulus. The ratio of longitudinal stress to the longitudinal strain is Young's modulus. Consider a wire of length N and area of cross-section A suspended from rigid support. Let delta L be the increase in length of wire due to force applied. Can explain it by in mathematically, that is y equal to longitudinal stress by longitudinal strain, that is y equal to F upon A by delta L by L, that is y into F into L A into delta L. Properties of Young's modulus. First, the value of Young's modulus for metal is large. Young's modulus for material of perfectly elastic body is infinity. Third, Young's modulus for material of perfectly plastic body is 0. 4. Steel is more elastic than rubber because elastic modulus of steel is greater than rubber. Second modulus, that is bulk modulus, it is denoted by B. That is, bulk modulus is equal to volume stress by volume strain, whereas volume stress equal to F by F upon A, that is divided by volume strain, that is delta V by V, that is V equal to F by A into V by delta V equal to PV by delta V. That gives us V equal to minus PV by delta V, whereas here we get the negative sign that we have given in the side note, that is negative sign indicates that as pressure increases, volume decreases. Compressibility. K equal to 1 by B, whereas K is equal to compressibility. 1 by B means 1 by bulk modulus, that is 1 by minus PV by delta V, whereas K is equal to minus delta V by PV. Third, shear modulus, that is denoted by G. G is equal to shearing stress by shearing strain, equal to F by A by delta X by N, or we can denote this as theta, which is a mathematical symbol in place of delta X by L. That gives us G equal to F by A into theta, or G equal to F into L by delta X into A. Elastic potential energy, that is denoted by U for the stressed wire. U equal to half stress into strain into volume, whereas stress equal to F by A and strain equal to delta L by L and volume equal to A into N, whereas F equal to force, A equal to area, delta equal to change in length and L equal to original length, A equal to area, L equal to length. That gives us equal to half by S into delta L, that is by due to the cancellation of A, F by A, where A is cancelled, and L in strain and A into L in volume. At last we will get the answer for this equal to half F into delta L. Elastic potential per unit volume, that is U equal to half stress into strain. For further calculations, we need to multiply and divide the first equation by the strain, that is U equal to half stress by strain and strain into strain, that gives half Y strain square. Y due to stress by strain, that is known as Young's modulus. And now, stress strain curve. Here, stress strain curve. Here in the diagram, we can identify a stress strain curve diagrammatically. At first, let's draw a stress and strain graph and denote the symbols as given in this graph. Whereas here A, B, C, D, and E are the 5 points, where A is proportional limit, B is elastic limit, or you can name as yield point, and C is the distance is a point between BD and D is a plastic deformation area and E is that last point fracture point and OA the distance between OA is known as elastic range and CD is plastic range and OF permanent set. So to explain this further, we have got some notes from reference books, that is study of stress and strain graph giving the following details. First, the region of OA is curved linear is linear. In this region, Hooke's law is obeyed. The body regains its original dimension when applied force is removed. The body behaves like elastic body. Second, in the region A to B, stress and strain are not proportional, but still the body regains its original dimension when the load is removed. The point B is called yield point. The corresponding stress is called yield strain. If the load is increased further, the stress developed exceeds the yield strain. The strain increases rapidly even for a small change in the stress. This is represented by BD in graph. That is, as you can observe the BD. So let's move forward. For a point C between B and D, the body does not regain its original dimension even if the load is removed. In this case, even when the stress is zero, the strain is not zero. The material is said to have permanent set. The deformation is said to be plastic deformation. The point D is the ultimate tensile strength of the material. Beyond this point, additional strain is produced, even by reduced applied force, and fracture occurs at area. If the ultimate strength and fracture points D and E are close, the material is said to be brittle. If D and E are far apart, the material is said to be ductile. Hence, you can observe all the points which we have explained in the diagram. Thank you. For more videos, subscribe the channel. Thank you.